Yeah, any questions? No? Okay. Okay, so one of the questions we have is, one of the questions I have is, how many samples do I actually need? Right, so one of the thing is, interesting thing is, if I try this whole procedure again, let's see how this probability is gonna change. So I'm gonna run in this again. You can see the probability I computed has changed from 1.24% to 1.22%, right? So which one is right? If I run it again, the probability has changed another time, becomes 1.25%. If I run it another time, becomes 1.27%, right? So the question becomes, how much can I trust this result? Well, this is actually the result of a lot of simulations, 1 million simulations, right? I mean, we have taken advantage of our simulation of this calculation is extremely simple. We didn't have to solve any differential equations at all, right? And if the simulation were expensive, I was only to say calculate, let's say 1,000 samples, then the result is going to be much more variable. So instead of always 1.2 something, I get a 1.1 something. If I run it again, I get 0.81%, right? I run it again, now I get 1.07%. So 1.92%. The result is a lot more variable if I decrease the number of samples. And of course, it's expected, because the less samples I compute, the more uncertain my result is. But how do we quantify that? How do we quantify how much we can trust in our result? That's going to be something we want to discuss, is basically right, how many samples should we use to compute our simulations? So before we do that, I want to introduce to you the idea that computing a probability is actually a special case of computing the mean of a random variable. Remember, we discussed in last week that the probability of an event, right? A is an event if it's a subset of the probability space, is equal to what I call the expectation, which is the mean of the indicator function I call IA, where IA is a random variable. So IA that takes a member of the probability space, right? So IA is a map from the probability space to real numbers. And in this particular case, IA is of omega is equal to either 0 or 1, depending on if omega is within the event A being a subset of omega, or omega not in the event A. So basically, IA is a random variable that is either 0 or 1, depending on if the event happened or not. Right? So we, in our Monte Carlo example, we have drawn many samples of this omega, and we have produced for every sample, we computed exactly if the event is going to happen or not, and our result is actually such an indicator function. So the probability is actually equal to an expectation. And our Monte Carlo method of computing the probability is basically the same as the Monte Carlo method of computing means. Okay. How many samples should I use? So that's the question we want to discuss next. So how many samples should you use really depend on how accurate of a result you want to get. And I want to basically look at the probability I compute. and emphasize that the probability we compute by itself is a random quantity, right? It's a random quantity because if I run the simulation multiple times, I get different probabilities. If I run it 100 times, I get 100 probabilities. And if the computed probability, remember, the real probability is not a random variable, right? I mean, the probability is a fixed number. Actually, if you are able to increase the number of samples to infinity, you would actually be computing the real probability. But of course, we cannot raise the number of samples to infinity. So we have to stuck with a finite number of samples. And as a result of the finite samples, the computed probability, or in statistics, is called the estimator of the probability, itself is a random number. So let's actually repeat the procedure for many times and see what this computed probability is like.